right. Hello, everyone. How is it going? My name is Coogan Brennan. You are on the Rollup courses. I'm going to be presenting on a topic. This is my topic today is what is a universal mental model for L2s? And we're going to get into all what that means. We're going to start with a little intros. We're going to talk about why mental models are important, particularly for crypto and L2s and zkAVMs. We're going to go through this universal mental model for L2s. And then we're going to do 3 important questions, kind of easy, intuitive questions that you can use to analyze L2s, and then do some questions afterwards. Just before we get started, I know that this course is particularly focused on ZKs. So this is going to be one click above ZKs, but I hope, I feel like there's a really important reason for that, and I'll get into it. It's also applicable to ZK stuff. So let's dive right in. So my name's Coogan Brennan. I have been in crypto since 2011, which is so long. It's like, it's dog years, right, for crypto. So that's, I've been in practically 70 years. Before being at Matter Labs, zkSync, I ran Consensus Academy at Consensus. Consensus is a software company that builds and runs MetaMask as well as Infura. So I was head of education for ran Consensus Academy, which is the education arm of Consensus. I am now doing head of education at zkSync, and my goal is to essentially do what we did for blockchain development for Consensus and with MetaMask, and with that initial rise of crypto. We'd like to do that now, sort of that knowledge mapping for L2s and zkAVMs and zkPs as well. So yeah, you can get connected with me here on LinkedIn, also on Twitter. Quick word on Matter Labs. We are the team that is helping to launch zkSync. It's a little bit of a confusing dichotomy. Another good dichotomy would be Off-Chain Labs and Arbitrum. So we're the team right now that is launching zkSync. Ultimately, it will be part of this community-run effort, decentralized governance, that sort of thing. But for now, we are a little over 100 folks who are located all over the world. And it's an amazing company, people from all incredible walks of life, just the most powerful, strong team I've been on in quite some time. We are hiring, so I'm going to put a link for jobs. If folks are interested, you should check those out. All different skills, doesn't have to be technical. And Matter Labs, we have launched a EVM compatible rollup, zkRollup, called zkSync. The full name is zkSync Era. We ran a testnet for a number of years called zkSync Lite, and that was also a zk EVM rollup, quite limited in its scope. Yeah, but we were the first zk EVM rollup to launch on Ethereum. It was pretty extraordinary. This happened back in March or April, I believe, this year, and it's been awesome. It's been a very, very cool ride so far. I assume that a lot of folks are familiar already with the scalability challenges of Ethereum and why we use L2s, but essentially we are moving transaction execution off chain and using Ethereum for data availability, and we'll get into what that means later, with the ultimate goal of reducing transaction fees and transaction times, while still maintaining the security of Ethereum. And again, we'll get into all this in just a second. We do this through this process of cryptography called zero-knowledge proofs, which can be used for a number of different use cases. We use it for data compression, but it's also used for privacy in networks like Aztec. And ultimately, Ethereum is the settlement layer, which acts as the custodian. Funds are always withdrawn from the L1. So this is where we get into our terminology of L2s. L2s always have an anchor in an L1, typically Ethereum, if we're talking about it today. So that's a quick intro into myself and Matter Labs and zkSync. I'm just going to speak really quickly on mental models. As I mentioned, I've been in the crypto world for quite a while, and I've been teaching blockchain development and crypto development for at least 5 years in a professional way. I've taught all over the world. And one of the things that is so important for emerging technologies, and this applies to blockchain, but also applies to AI, any other sort of emerging field, it is so critical to have a mental model, which we're defining as a lattice work on which you can hang knowledge. And the reason why it's so important is because if we have a framework for understanding the world um, that is flexible and resilient, then it not only means that we're able to understand the system that we're looking at, in this case, blockchain or L2s, but we're also able to receive new information about that system and it doesn't break our understanding, right? We have a flexible and anti fragile model of the world. And uh, as I've been teaching for blockchain, I've found this is incredibly helpful, and it's useful on a broad scale as well. There was a study that was done a couple years ago at Stanford around multitasking, sort of seeing like who's good at multitasking, and anyone who's read the book Thinking Fast, Thinking Slow knows this story. But essentially, they were studying multitaskers, and they looked at the best multitaskers, and they wanted to sort of gauge their attention. And what they found out is that people who are multitasking are actually have a quite poor attention span. And the reason why is that they're worse at what you call mental filing, keeping information in the right conceptual boxes and being able to retrieve it quickly. This is from the study. In other words, their minds were more disorganized. So, what we're going to do today is going to be sort of giving you a mental model, an organization system with which to understand the L2s and zkEVMs. So when you hear about folding schemes, or when you hear about sequencers, or when you hear about smart contract security, or when you hear about bridges, you understand where that information goes. I think that's really critical as a base layer knowledge, which then allows you to have a very productive and extremely beneficial career and just way of navigating and comparing these systems in crypto. Um, and so this is an example of one of those mental models that we build at Consensus for blockchain development more generally. You can take a look here, and essentially, kind of as people were learning the process, they would just be able to slot in, okay, I'm learning about Ethereum clients, that goes here. I'm learning about DAOs and DeFi, that goes here. I'm learning about JavaScript tooling, that goes here. So we're going to build the same sort of system here for you all around L2s and zkEVMs. And I think that's all we want to say about that. Yeah. Oh, this is just another sort of example of another sort of framework. A roadmap is another way to think about it. Being able to understand the different kind of paths that one can take to specialize or to better understand a field. This is a really successful or really popular DeFi developer roadmap from a GitHub repo, which you can find pretty easily by Googling there. Alrighty, so onto the topic of today, which is the universal mental model for L2s. So as the L2 and zkEVM space continues to grow in popularity and technical innovation, it's really critical that we have these mental models for all the reasons that we spoke about, as well as being able to compare and analyze these systems. So there's a lot of different networks and a lot of different projects that are coming out, and ultimately I would say, 97% of the population has to just trust what they read on crypto Twitter, or what they read on blogs, or what they read on repos about technology, rather than being able to understand it for themselves. And the promise of crypto is something very different, right? The promise of crypto is you don't have to trust; you can always just verify. And so, it's so critical to be able to trust and kick the tires, to not trust, to kick the tires, and to verify these different L2 projects as they get launched, and they promise airdrops, or whatever the case may be. It's really important that you, as someone who's a developer, or someone who's trying to understand the system, the ecosystem better, is able to very quickly and efficiently and comprehensively gauge, is a network good? What are the trade-offs of this network? And what are some trapdoors, or what are some sort of things that I should look out for when analyzing networks. So we're going to dive into this model here that we have now. This is both simple and complicated, but we're going to go through these sort of critical components, each of which in our mind represents a group of components and elements that define essential aspects of any layer 2 network. And this includes zkSync era, this includes Arbitrum, Optimism, Starkware, Linnea, any sort of project that launches, you can use this this mental model, this diagram, to analyze these points. So the critical points that we're going to be touching on are the things where you can really profound sort of say, okay, here's the sequencer commitment to mainnet of data. How are we going to understand that? Hold on one second. Wonderful. So these are sort of like the sort of the almost like the choke points, or the points where you can like really discreetly see, okay, these are the points of difference of networks, L2 networks. So let me use that to compare how these networks are different or the same, that sort of thing. The diagram is very simple. There's this phrase from the statistician George Box that goes, all models are wrong, but some models are useful. So we are abstracting away a lot of complex information in the hopes of providing this broader understanding and tool for analysis. But you can fall down a number of different wormholes and sort of side quests as you're going through this material. If something sort of strikes you as compelling or interesting, you can go deep into that area. Any one of these areas, there's a lot of simplification that happens. So yeah. So let's go. Let's start. Let's start up with our first one. So the first part of an L2 network is the onboarding of the user, and this one is from the user's perspective. It's fairly straightforward. Usually just bridge your assets, but it's really important as the user, you're able to understand the bridge, which is the way in which those funds are, the way in which you migrate funds from L1 to L2. So the onboarding is an interaction with a smart contract, which is a bridge, and the bridge is responsible for safely securing or locking up assets on Ethereum mainnet. And it's crucial because it's the linchpin of security for those assets. As we mentioned before, the sort of the promise of L2s is that you can dispute issues that happen on the L2 on the L1, and that predominantly happens either in or with the bridge contract. So the bridge contract is going to be really critical. You're going to want to make sure that's very well audited. You want to make sure you understand the process and that and the different methods of dispute, which we'll get into a little bit later. When the assets are locked up in this bridge contract, the bridge creates a counterpart on the L2 side within the rollup. So the L2 tokens are the sort of inherent, they carry the same inherent value and utility of the L1 token, in this case ETH and the Ether token, but they have the added benefits of the layer 2, which is typically faster transaction times and lower fees. Other networks add on different capabilities as well. So for example, zkSync has native account abstraction. And so you're able to kind of supercharge your L1 assets, in this case, ETH, by introducing account abstraction on top of it, with still maintaining the security features of Ethereum. So onboarding, pretty straightforward. Transactions, again, this is a pretty simple one, so we won't spend a whole lot of time on it. But essentially, the transactions look exactly the same to the user, right? The only sort of that's actually sort of this like big part of it is that, let's say you're using MetaMask, like it's going to look exactly the same of a transaction lifecycle. Maybe the confirmation happens a little bit quicker, But the transactions look to the user exactly the same as they do on L1, and maybe a little faster and hopefully a lot cheaper. And that's sort of the goal, right? You shouldn't be able to tell that you're on an L2, except for being able to check on the MetaMask network modal button and seeing, oh, okay, I'm on this other network now. So it's really, really important that's sort of invisible to the user in some ways. But the really critical part of those transactions is that, it gets submitted to a mempool, which is similar to Ethereum. But rather than being collected by miners, it's collected by an actor called a sequencer. And this is a really, really critical part of the process. The sequencer is the is a really important actor within the L2. It collects these transactions, it orders these transactions, and we'll get into that in just a second. But just know that the sequencer is kind of the main collector of all the transactions within an L2 network, and yeah, it's a really critical part of the whole L2 system. So we have covered onboarding the user here. We've covered transactions, submitting transactions. And now we're going to go over what we're calling computation and aggregation. So after the transaction that we just saw is signed and submitted by the user, the next stage involves the sequencer computing the updated state of the L2 blockchain network, assuming that these transactions go through. So it's very, very similar in terms of the outcome of the EVM, but the Ethereum virtual machine and the way that it happens on layer one. But the way in which that computation happens is really, really different. And this is the first big, big important difference on L2s that we'll get into. So the essentially there are two broad forms of computation and aggregation process on layer two. So again, just to sort of reiterate the point, when we say computation and aggregation, that means the sequencer is collecting those transactions that we just saw from the user. It is computing those transactions, making sure that they're valid, making sure that properly signed, all the stuff that you would also do on an L1, and then it's making sure that it's showing the reflected L2 state. This is the new state, assuming that all these this transaction goes through. Okay, and so it's assigning a balance from the Rollup Twitter account Ethereum address to Coogan's Ethereum address. Changing those balances, that sort of thing. That's what's happening sort of in effect. Now, how we get there is different. There are two broad ways in which L2s computate and aggregate transactions. And they're symbolized here by the OP, which is the optimistic process of aggregating and processing transactions, and then our logo, but representing the ZK, which stands for zero knowledge, way of computing and aggregating transactions. So this is a more detailed breakdown of that. And so we're just going to address the optimistic computation aggregation, then we're going to go into the ZK process as well. So the optimistic sequencers collect transactions and they collect them all into a block. And then they assume that the transactions are valid. They naively or optimistically process the state change of those transactions as though they are valid. So they don't actually they don't actually sort of check to make sure that there's no fraud happening or there are no issues. They just sort of blindly assume that that's what's happening. So, if that was sort of the end of it, then that's a huge trust assumption, which could be easily exploited. But optimistic rollups use a mechanism known as a fraud proof. It's also called a fault proof now, but the common term is a fraud proof, which is the main protection against against any fraud happening. So the fraud proof is essentially a security aspect that is a challenge window during which users are financially incentivized to check the validity of the transactions. And we'll get into that in just a second. But it's just really important to know that is the sort of the main mechanism that's guaranteeing the security of these networks, is that staking mechanism from a sort of a watcher, a community of watchers that are watching the network. You know, computation and aggregation on these networks, on the optimistic networks, are not actually dramatically different from Ethereum mainnet. In fact, I think a number of optimistic networks just use a fork of Geth as their client, their Ethereum client, which is the main Ethereum client that you use on mainnet. And so that's just sort of important to note that there's not actually a whole lot of change in terms of the computation and aggregation. Now, so that's on the right hand side, I believe, is the optimistic process. On the left hand side, you see the zk method of computation aggregation. This is where it gets really interesting, and obviously the basis of this course and why we're here. So the sequencers for the zkRollup also batch the transactions into a block, but rather than relying on this fraud-proof ecosystem, the zkRollups use a form of cryptography known as zero-knowledge proofs to generate a single mathematically irrefutable proof to validate the execution trace of those transactions. And what that means is it's essentially with a single sort of digital signature, let's think of it, we are able to, with that single digital signature, so how about this? I've heard that a good analysis, a good sort of comparison of the zk cryptography, like actually explaining the cryptography, is a digital signature, which in Ethereum it ultimately sort of shows that that a certain someone actually has signed a transaction, right? That's what a digital signature shows. Someone who's holding a private key has signed the transaction without revealing anything about the private key. Zero knowledge proofs, the proof itself is like a digital signature, but for that entire block of transactions. So rather than just that single action of saying this person has signed this transaction, the zk proof is vouching for the entire block of transactions, which is huge. It's an enormous amount of execution, which captures a lot of information very succinctly. It would be really expensive to do on L1s right now, so we pull it off and we do it on our own network on L2s. But it creates this enormous amount of compression, and this is the kind of the real magic of zk's, and the reason why it's really so critical, and the reason why even optimistic networks at this point, even Optimism Network says we eventually will have to use zk proofs for this reason, which I'm about to describe to you, which is that zk proofs provide recursive, they provide how do I say this? They provide non-linear scaling. So with optimistic networks, you can only scale as many sort of people you have on the network, because it's the same thing as just running a single validator. You can't scale that in the same way. Like the amount of effort is rises with the number of people that you add to the network. For zk proofs, because there's this compression that's happening, you get this exponential growth of scale that you can do on networks. So suddenly you can really, really compress a lot of transactions into smaller proofs. Now, right now, those proofs are very expensive to compute. So it's not, doing recursive proofs is challenging at this point. But the technology is there, and we are doing that work to be able to discover it. And it's just, Vitalik has said this is the way of the future. Optimistic Rollup said this is the way of the future. So if you take one thing from this talk, take that the zk method is the way of the future moving forward, just plain and simple. Yeah, so that's sort of our overview of those two systems, those two different ways of computing and aggregating data on L2 networks. Going back to what they have in common, both regardless of optimistic or zk processing, both create this unverified L2 block. And this is known, then you can see this little line here that's going down, and it's going to this L2 state contract, which is also our bridge, the way that we used it to come onto the network. But it also enshrines the L2 state on the L1. This is called the soft commit, and this is not very well understood, I think, generally speaking. But that proof that we just talked about, the zk proof and the fraud proof mechanism, comes as a secondary separate mechanism. It's not included with this soft commit that the sequencer passes to the L2 network. Those are two different functions that get called, at least with Arbitrum and with zkSync era. But I'm almost positive with other L2s as well, regardless of optimistic or zk. And essentially that's why, even though it might take a lot of time, like a week for fraud proofs, or a number of hours for the proof on zkSync, if you do a transaction on MetaMask, it doesn't take a number of hours, or it doesn't take a week to confirm. It confirms in a matter of seconds, because the wallet and the nodes are watching the sequencer doing that soft commit. And we're assuming that that's going to be the case. So that soft commit is actually quite important for transaction ordering, for user experience, all this sort of stuff. But it's actually separate from the staking, or the sort of security mechanism. Now, zkProofs are not doing naive computation, so there's that difference there. But that's how we're able to sort of confirm, quote unquote, confirm transactions quickly on MetaMask, even though that we might not be able to withdraw the funds from those transactions in a matter of hours for zkRollups, but a matter of a week, or at least 7 to 10 days for optimistic rollups. So we've just gone over onboarding, transactions, aggregation, and computation. And now we're going to talk about this this kind of interesting element of the process, which is the commitment phase. So we talked about just now, kind of why there's this final confirmation, and this sort of this L2 block that goes to the network that updates it. But there's a real critical part of this process. So every layer 2 has to update the L2 state root that's on the L1 smart contract that we saw on this earlier slide right here. This little bar down here, it says L2 state contract. But the way in which it does it, because we're going to be discussing this dispute mechanism in a second, because of the way it does that, there needs to be extra data that is also provided along with updating that state root. Because not only do you have to sort of update the state root for the smart contract, but you also need to provide information about what led you to update the state to look exactly like that. And you need to do it in a way that's compressed, because otherwise you're just doing the same thing. You're just sort of burdening the Ethereum mainnet layer with the same computation that we're trying to pull off of it. So this is, again, after that sort of the computation and aggregation, where we separated between optimistic and zk. This is another really critical bottleneck, a really critical decision, sort of design trade-off space of how a network decides to do this. So not only sort of how they're computing and aggregating it, but then how they are providing that information to the L2 to update their state root. That helps us better understand the network and a way to do that. So one way in which that's done, here we go. Let me show you here. Again, we have this sort of distinction a little bit too, because certain networks, the optimistic networks, need a certain amount of data, and zk need a certain amount of data. But again, it's just even within the zk space, there's a difference in that. So the optimistic mainnets, you want to make sure you can properly challenge the L2 transactions. Because of the optimistic assumption, the commit then challenge mechanism. So all the transaction data has to be readily available on layer 1, because if there's a dispute on the layer 2 network and we want to pull that fraud proof, you have to be able to reference L2 transaction data on L1. So in optimistic rollups, you have to publish the entire set of committed transaction data, even if it's in a compressed form. And it has to be published on chain, meaning as part of a transaction to your L1. And then during your challenge period, this week-long area during when you're doing your fraud proofs, or allowing for people to see if there's fraud on the optimistic network, you must be able to sort of call up that data to reference fraud that happens. Similarly, alongside that, the person that is going to attest to the validity of the state transition on optimistic rollup has to also create a bond, sort of a stake on the L2 block that they submit. They say, we're going to say this is the state transition that happens. If someone is able to to challenge that during the L2 during the challenge period, I'm going to forfeit this bond. So again, that's part of that sort of game theory mechanism that we spoke about earlier. That's securing the optimistic rollups. And just to explain this before we jump into the zk, this is just an example of a layer 2 collecting transactions at the very top, batching it up into a single transaction, and then committing that to layer 1. And then if you can see here, there's a Merkle tree here. And apparently we get into Merkle trees a lot in great depth later on in this series. But this is essentially sort of illustrating that there's a Merkle tree that gets updated on L1 that represents the state on L2. And that's part of that dispute mechanism. So the other flip side, though, is how zk's make that commitment to the state changes on L1. So layer 2 transactions that are validated by zkProofs are mathematically guaranteed to be correct. Therefore, we don't have to worry so much about transaction disputes. There are certain sort of edge cases where you still need to figure that out. But really, no corrupt transactions can be proven, mathematically proven, on the L1 chain. So literally, like if there's fraud on the L2 chain, it just won't compute on that state root that's on the L1 chain. So if there's that issue, so if we don't have to worry about that, so what do we actually worry about then? Well, the zk rollup, then we need to be concerned about what they call censorship, transaction censorship, and censorship resistance is the other term. And it's a little bit confusing because we talk a lot about sort of censorship in the case of social media, but this is a little bit different. Essentially, as we talked about in the diagram, let me see here. So you can see we got the sequencer here that's processing all these transactions and putting them onto, in that block, which then goes onto the L1. Let's say that sequencer goes down, or let's say that sequencer is corrupt or, corrupted, meaning that it can't process any more transactions. The zk rollup, to preserve that sort of quote unquote L1 security, needs to allow the users to bring their sort of disputes directly to the L1 without going around the sequencer. So that's a big part of the concern when we're sort of publishing data. So the way that zkSync does it is that our rollup L2 blocks, we don't have to include all the full transaction data along with the zk proof because we're not doing that sort of transaction dispute. But what we are doing is we want to sort of commit we commit what is called like the state diffs, essentially sort of the account differences before and after this L2 block is being committed. And that way, theoretically, you can go back and as a user, I can show, listen, my account changed like this, like this, like this, like this, like this, right up to this moment where the sequencer died. And so I want to pull out that remaining balance, and we can all agree on that on the L1 that's my balance. I don't have to dispute the transactions. I can just immediately pull that out. And so this is a really, really critical part about that is understanding how a zk rollup, such as Scroll, such as zkSync, such as Starkware, allows for that censorship resistance to be built into its protocol. It's really, really important to understand that. Again, because we don't have to worry so much about transaction fraud because the transactions are mathematically guaranteed. What we have to worry about is the censorship resistant part of it. This is just a quick diagram, just sort of talking about the proof and sort of going over like what is that actually, what we just sort of talked about, the L2 block, what goes into that proof, what is a part of that process. The other thing that we want to highlight that I talked about earlier was we're essentially dividing up the sequencer and the prover actions in the L2 rollup. So it helps sort of logistically and sort of as a mental model to separate those two because they're different. As we can see here, they're different roles. One is about state transition, and then one is about sort of guarantee of that state root commitment, and then being able to contest or be able to save or recover those funds in the case of some sort of sequencer corruption. Alrighty, so that is, we talked about computation aggregation, the submission and the commitment aspects, and call data, the data essentially that's required to go to mainnet. Now we're going to talk about something called data availability. This is another sort of weird sort of buzzword that isn't necessarily the most intuitive process. So we're going to get into that a little bit. And this diagram here is talking about is just going to be a representation of that data availability. So again, we have the smart contract that's on layer one. So here it's Ethereum, and it maintains the L2 state root, that smart contract. And that smart contract is getting these periodic updates from our L2. It's getting the sequencer information, then it's getting the prover or the sort of the fraud, the validator from an optimistic rollup, getting that assertion from the validator. But all the L2 block data, like all the stuff that's getting copied, and I'm actually gonna put a link here. Let me see if it'll let me put a link in here. All the L2 block data that's being consumed by the contract is by default posted in something known as the call data field of an L1 Ethereum mainnet transaction. So I'm gonna put one of our sequencer updates. Let me see. Actually, I might have to put it in later. Um, no, here we go. I got it. So if you go on Etherscan and you look at this transaction, this is from actually the zkSync node going to the L2 state root um, on layer one. And this is the actual, if you go to on Etherscan, you go to more details and then input data and then decode input data, you see this field here. And so you can see all this really interesting, this almost looks like a block header, right? On an L1 network, but this is actually an L1 transaction, right? But it represents all these compressed transactions that are happening on the zkSync network. And there's all these different fields, block number, block hash, number of L1 transactions. These are that sort of censorship resistant or bridging transactions that are happening. We have our commitment here, and then we have the new block data. So all this stuff gets consumed by the that L2 contract that's the state root contract on L1 and is able to process it. But this input data is super, super important because it captures all the like this is the reason why layer twos can claim layer one as the base security layer. Because we are by including all this information in an Ethereum transaction, we're also committing that to the Ethereum state. And so if we do need to have some sort of dispute, and again, this is similar for optimistic rollups as well. If there's some sort of dispute, we're going to be pulling this data that you're looking at right here, this call data to do that kind of processing. And where's that going to be stored? That's going to be stored in Ethereum clients. Ethereum client data storage is could be its own book that we could write about. But essentially, it is a really uh, it's just sort of a canonical way. Like we can assume that this is data that's going to be around for forever. And it's really critical. And so when people talk about data availability, the real question is kind of like, where does this data, this call data, where is this captured in a way that can be pulled up? And if it's on an L1, then we call the L2 an L2. There are other options for that, which I'll get into in just a second. But I want to just sort of underline one more thing, which is that L2 is using Ethereum for data availability is so important that the next big Ethereum core, the next big Ethereum hard fork, the network upgrade, is going to develop an entirely new transaction type to accommodate the data updates like this from L2s. Because quite frankly, this is very expensive to do on L1, and so it's still L2 transactions are very expensive because you're distributing the cost of committing this data to the L1s to anybody who's has their transaction in that L2 batch. But the same sort of upgrade system that brought us the merge, that layer, that level of protocol change is happening for data availability. It's called EIP 4844, and it increases the amount of space available from about 500 to 100 kilobytes per block to 1 megabyte per block. It also creates this separate market for the data and a sort of a new data type for transactions, and this will allow L2s to dramatically lower costs because the data availability, the commitment costs for pushing this data onto L1 will become much more affordable. Yeah. And just to sort of spin your head just a little bit more, if you turn data availability in sort of a different direction, like if you pull like if you commit that data, that on-chain data, that transaction data to something that's not an L1, then we get into this discussion around L3 systems, layer 3 systems. So this is again kind of out of the scope for this talk, but to fall down this rabbit hole if you'd like to, you would commit that data to maybe another network, maybe an off-chain server, something like that. We're not going to dive into it that much, but here's a sort of a slide deck, and there are multiple sort of rabbit holes you could fall down just by googling anything on this slide right now. So again, when you hear the terms L3s or you hear the term data availability, just remember that it's all about sort of where is the data stored that allows you to recreate state for the L2 contract. Okay, so we're coming up on time. And that is sort of like we have covered the kind of overall components of a system that everyday users will interact with in their in the like typical user flow. There's also as you can see here, the sort of aspect of forced transactions that are here, which we weren't able to get to, but are really important. And then network upgrades and maintenance is another aspect of it. But I think we're going to stop there, and yeah, I think we're gonna stop there just because it's a lot of material, and I just want to make sure that we have and folks don't get overwhelmed with information. So yeah, all right, that's all from me.
Amazing. Thank you, Coogan. Yeah, that was a great overview. I think we both stayed high level and dove into some of these rabbit holes that are seemingly endless, but did a great job of unpacking them and explaining the relationship between these components. So with that being said, I'd like to start at the high level because
Sure.
we talk about mental models like relatively frequently on this channel, but this is the first time where we kind of heard like an analysis of mental models without applying that to something. So I think I can control these slides here. And I'm going to go back to the slide that you had on the organizational pattern of mental models, because that was fascinating. So I find myself thinking in blockchain sometimes. And what I mean by that is like, sometimes I think to myself, like, okay, this thought is a transaction that is like going through the blockchain of my mind. And like, where do I settle that transactions? Well, sometimes I post that call data to my memory. And I'm like still kind of like abstractly thinking about these ideas and how to use blockchain as like an organizational pattern for organizing my thoughts. So I'm curious if you've like tinkered with this a little bit. Have you like had some similar like realizations of how to structure our mental processes for the most efficiency and security of our ideas?
Yeah, that's it's a good talk. It's like thinking about thinking, which is my favorite kind of thinking. Uh so I love that you think about your life in terms of blockchain data structures, because I don't think they're necessarily the most efficient data structures, like they're exciting for like trustless interactions and settlement stuff, but so I love that. I've never heard that before, and I think that's excellent. But yeah, I do think that two things. One is that I'm going to include, this is like a little bit off topic, but I think it's really important just because you bring it up. There's this great blog called Farnham Street. You all might be familiar with it if you're familiar with mental models. But it's essentially sort of talking about, I'm using the term mental models quite generally to sort of be like essentially this kind of structure, almost like its own data structure that you can slot things into. But there's another understanding of mental models, which is, different people have different mental models of understanding things. So the mental model of like relativity, or the mental model of second order thinking. It's this really, really helpful way of being able to process information. And it's really, really critical, as particularly for folks who I think will be watching this, because typically folks, and myself included, in crypto or blockchain are self-taught, and there's just a fire hose of information coming at you all the time. As soon as you feel like you've got everything, you got everything up to speed, you have to go to sleep, and then you wake up in crypto Twitter, something else has happened in another part of the world. So it's so important. Like, you could just try to consume everything humanly possible, which you can do for a while, I think, for if you don't have to sleep, but eventually you do, and eventually other things will come in. And so I just think it's incredibly important to have these models, because it allows you to um just think better and be able to have that sort of anti-fragile quality to your information processing and your digesting, which is the fun part about crypto, but also the exhausting part, but mainly the fun part, which is that you're always learning something. You're waking up, and um, one of the reasons why I'm excited to be at Matter Labs is that I didn't really understand zero knowledge proofs. I didn't understand hardcore cryptography, despite having been in crypto for a long time. And so I get to learn something new about that, and I get to come sort of share it and find good ways to sort of explain it to folks. So um, yeah, I'm not sure if this answers your question, but I do just think that for crypto in particular, having these models and these ways of like you said, relating it to everyday life, that's a helpful way. But being able to just sort of have some sort of framework in place will save you a lot of grief, a lot of mental effort. And yeah, I could talk about this for a really long time, but I won't. But yeah, I'm glad you guys talk about it a lot, and it's really, really important. And yeah, yeah, I'll yeah, that's
Yeah.
all.
More of a abstract kind of meta personal growth and kind of overall ability to live a successful, happy life
Right,
kind of vibe, which
right,
is
right.
important. It's like what's
Yeah,
what we're all trying to do here.
of course. Yeah, absolutely. Yeah, absolutely.
More so on the tech side, I was gonna pull one up here, actually specifically on this one that unfortunately you didn't finish. Whether is this one or the other one, the primary tech question that I had, which is
Yeah.
way different than where Rob was at,
Yeah,
was
please, please.
forced transactions. How does that happen, and what does that really actually mean when a sequencer forces transactions
Yeah.
to the L2 state and then back to L1? Is there a difference between like forcing those and then just like doing like a normal batch to L1 or
Yeah.
yeah.
Yeah, so it's a really good question. So, the question is around this particular sort of this quadrant of forced transactions that we weren't able to dive into, that we weren't able to dive into. And if I'm understanding your question correctly, it's, where, how is a forced transaction different from a sort of a sequencer, traditional, like the L2 blocks that we talked about? And I'll answer your question by actually going to, I love that we're like running around the slide deck. This is great. I didn't think we would use it this much, but okay. So this is the block that's submitted, right, by the sequencer, by the zkSync sequencer. And if you look at there's a field here that I mentioned called L1 transactions. I can't find it. Where is it? Here you go. Number of layer one transactions. Do you see that? It's like fourth from the top. Do you see that there? Yeah, can you see that there? Okay. So this is typically this is bridged funds, right? So an L1 transaction is typically someone bridging fund on L1. I'm putting funds onto zkSync L2, or any other L2. But there's another kind of L1 transaction that can happen, which are these forced transactions. Now, they wouldn't show up as anything different. They would still look like a layer one transaction here on this thing, right? It would be like, rather than 9, it would be 10 if we included our forced transaction here. But there's this kind of special way in which, so there's a special way in which those transactions are processed. It's almost like a sort of like a side channel, or like an emergency exit. before actually putting all this slide together, I thought it was something that the user directly submitted to the L1 state contract, but it's actually something that goes to the sequencer, which is why it's really important to have decentralized sequencers, because it seems problematic. Like, how could you force a transaction if the sequencer, which for all L2 networks right now, the sequencers are centralized, or all all ETH L2 networks, it's centralized. So how are you going to do this forced transaction, which I think is sort of a part of your question. And the answer is that we have a decentralized sequencer now, like a sense of like you could download the repo and run it. We're going to sort of unveil that at DevConnect in November. But essentially, the smart contract expects data in a certain format, and so it's going to grab those compressed transactions, which are the sort of the quote unquote traditional L2 blocks, but it's also going to pull in these sort of L1 transactions, which kind of creates a new, if it's bridge funds, it creates a new account essentially, and sort of adds that to the Merkle tree, the state root that's there. Or if it's a forced transaction, then it kind of follows that other path. I was saying, okay, we just got to do a quick release of these funds to that user that's on L1. But kind of confusingly, all of it goes through the sequencer. And the reason why that sort of censorship resistance is that, the sequencer also has to be open sourced, so that, Andy, if you wanted to include this, but the sequencer was down, or zkSync said, you know what, we're actually not running valid blocks anymore. We're forking the network. We're doing something else, kind of like Ethereum Classic or whatever. And you're like, no, I want to sort of pull it out on the network at the last valid block. You would then spin up a sequencer. You would generate a valid block, and you could quote unquote submit that to the L1 contract. In the same transaction, that like this Etherscan one that I put in the chat there. Does that make sense?
Yeah, no, I think it for sure does. It's the key differential is the different types of like effectively inputs or the transactions, right?
Right.
As you said, there's those kind of like L1 ones, and then there's like the original L2 ones, bridge funds. This is probably a different segment, but there's different types of tokens on different
Right.
bridges and different chains. And I guess my follow-up would be that is this something that users have to pay more for, or is there often a reason for the expediting of this?
Oh, for a forced transaction?
Yeah, like, is it something that I can control and like pay more to accomplish, or it just
Yeah.
kind of happens?
Yeah, you can. That's a good question. It does cost more because it's a not compressed. Part of what makes L2 transactions cheaper are that they're clustered. They're compressed, so it's going to be more expensive. It also will be processed at on the L1 level. If we can sort of imagine, if that makes sense. And then I know on Arbitrum it's called like the inbox, and then on Linea they have like a mailbox almost. Like, it's also used sometimes as like a messaging service as well. So again, it's more in terms of the mental model, maybe like that sort of inbox might be a better one. It's sort of like an inbox in that contract, where the transactions are more expensive, but maybe there's a reason why you want to be sending transactions like that on your network, just from L1 to and bypassing the traditional compression. Maybe there's some sort of aspect there. So again, this is one of these sort of simplified models where this forced transaction path, and it, like I think you're pointing out, doesn't always have to be kind of aggressive, or this kind of it doesn't always have to be like the sequencer is down or the sequencer is corrupt. It also can be some other sort of reason. But the main sort of takeaway is that this exists. This sort of like separate slot of transactions exists. Different networks use them in different ways, and how a network implements that is the sort of the design trade-off and that sort of trade space, that you would understand it in different ways. So it's like that thing is there, and then it it's sort of, there's a whole spectrum of what's possible within that design. Does that make sense?
Yeah, that covers the entire scope of why I was curious. Had not heard of that at all before.
Yeah. It's an interesting kind of weird little, but different networks do different things with it, which is kind of cool.
I think Rob's gonna probably wrap us up here unless he's got another question. I want to be respectful of your time, Coogan. Thank you so much for coming on. Rob, do you have another one or?
Yeah, I think maybe just one more.
Yeah.
On another, so a lower level question here.
Sure.
On a similar note to the flow of what ends up on L1.
Yeah.
I noticed in this diagram that the proof is not published to the layer 1.
Yeah.
Is that unique to zkSync or is?
No. So sorry, there should be a line there. Yeah. So sorry, that's just like the diagram is missing a line, which is absolutely chaotic that I would do that and bring it on here. But there's a version. Maybe we could, if you could mark up the thing, you know. Yeah, that is that should be a line there.
Okay. No worries.
Yeah.
Just making that clarification.
No, I appreciate that.
Proofs are published to the L1. Maybe you could just
are
explain
published
that
to that. Yeah, absolutely. So imagine viewer that there's a line there between the proof and the L2 state contract. But essentially, like we said, the sequencer is submitting these blocks of transactions to the network, but the way in which and that block of L2 transactions and those L1 transactions that we mentioned, there's a state transition that happens, right? So there's a state before that block and there's a state after that block. And there's a certain kind of assertion that needs to be made about that state transition. From the zk side, we make a mathematical assertion. We submit a proof that says, here's a proof that shows that mathematically this state transition occurs, similar to a digital signature, like we said. For optimistics, and they don't call it a proof, but again, if we're trying to sort of simplify things, but for optimistic rollups, they use what are called assertions. So there's an assertion of state. So the validator, again, it's a separate sort of function. The validator says, I'm asserting that this is a stake, and that this is the new state, and I'm going to stake, ETH. I'm going to stake money on it that this assertion is true. And if someone else is able to come in and say, hold on, I don't think actually that's the correct state, then that's what triggered the whole fault proof, fraud proof mechanism, and that starts the whole challenge process. So that's the they don't call it a proof in optimistic networks, but it's an assertion. But that's essentially the kind of the validation. So if you can think about the state transition and then the validation of that transition as two separate entities, the transition is that sequencer block getting submitted, and then the validation is that proof or assertion from depending on whether it's an optimistic or a zk network.
Got it. That makes sense.
Yep. And again, apologies for that. Just like absolute madness. Just, some men just want to watch the world burn. That's like, why would I do that? Okay. Just really quick before I go, I do want to cover these because I think there's a lot of data that we just sort of covered on that diagram, but I think that there are like 3 easy questions or like kind of simple questions that can distill a lot of these different sort of points that we've been going over this past time. The first one is around the computation, aggregation, and commitment of the network state. Is it optimistic or is it zk? That's the first easy question. And again, it's going to touch on those design points, and there's this implications that we've gone over on the network itself. The second one, how do users rescue funds? And this is actually sort of what data is included in the L1 state root updates, and what are its dispute mechanisms, or as Andy pointed out, what are the ways in which L1 transactions can kind of find their way to the L2 state contract. So by understanding how a user can rescue their funds, or perhaps just sort of directly speak to the L2 state contract, that will illustrate to you the design decisions and the trade-offs that the network made around the data availability and its dispute mechanisms. The last section is, where is the data stored? And you can sort of add a sort of and what kind of data is stored. So optimistic networks have to include all the transaction data. It could be compressed in some form. zkRollups have to can provide a much more compressed version of that data. So we want to know, what is that data, and then where is it stored? What's the data availability layer? And that will go back to the dispute mechanism. That'll also go back to computation and aggregation. Again, it's a very simple question, which sort of captures and touches on a number of different elements within that diagram, that sort of L2 mental model, the universal L2 mental model. So easy questions that I always really appreciate having that. So if someone's giving me a talk, or they're pitching their network, I can have in my mind these questions, which which can tie back to this mental model, which allow me to very quickly kind of get my orientation within that network itself. And that's extremely valuable for the reasons that we talked about earlier. So yeah, with that, Robbie and Andy, I'm official. I'm done. I promise. I'm done for sure. If folks want to follow me on, you can follow me on LinkedIn or on Twitter there, or send me an email if you have any other questions.